and most welcome to post-blog station. So I welcome Dr. Hiran. So Dr. Hiran is with us. Dr. Hiran, you are most welcome to our team campus, but virtually. So we are unhappy today because we are not inviting you physically, the campus. So I request Dr. Sushruta Mishra kindly introduce our today's session speaker. So Dr. Sushruta Mishra, this is yours, please.
Yes, sir. Thank you, sir. Good afternoon, everyone. We'll proceed with our next session. This session is an interesting one that addresses the cardiac healthcare using machine learning techniques. And to discuss this, we have with us our eminent speaker, Dr. Hiren Kumar Thakkar. Now, Dr. Hiren received his MTech CSC degree from IIIT Bhubaneswar in 2012 and PhD degree from Department of Computer Science and Information Engineering, Chang Kung University, Taiwan, in the year 2018. Later, he worked as a postdoctoral research fellow at Motor Behavioral Research Lab of Healthy Aging Research Center of Chang Kung University, Taiwan. Currently, he is working as an assistant professor in the Department of Computer Science Engineering, Bennett University, India, from 2019 onwards. Dr. Hiren has published many SCI journal papers, including in reputed journals like IEEE Journal, on selected areas in communication, IEEE sensors, information processing and management, Elsevier and sensor journals also. He has one patent published to his credit also. His area of expertise is the application of machine learning and deep learning in healthcare domain, especially in cardiac healthcare. His research interests include the areas of biomedical big data analysis, cloud resource management and optimization, and machine learning. More recently, he is actively working in the area of reinforcement learning. Dr. Hiren, I request Dr. Hiren to take the stage and please carry the session forward.
Hello, Dr. Hriday Kumar Mishra and Dr. Sushruta. Thank you for having a wonderful introduction. And I'm delighted to join this faculty development program. And thank you for giving me an opportunity to present my concepts on the healthcare data analysis using machine learning. And it's very nice to see that a lot of people has joined. Already 57 participants are there. So it will be a very fruitful session for me as well as for the audience. And I hope there will be a healthy question answers following the session. So let us, without wasting the time, let me share the slides and start the session. Okay. Please give me time to share the slides.
Is it okay, Dr. Hiran? Could you able to share?
Yes, I'm trying.
Okay. Yes.
I hope is it visible?
Yes, good.
Yes.
Let me go. Okay, so we are now in a full screen mode. Okay. So, guys, we are today going to discuss the cardiac healthcare data analysis for designing early warning system using machine learning. So before jumping into the nitty-gritty of the concepts, I would like to bring the notice of the audience that what we are supposed to do here is that the main concept of this healthcare data analysis to design the early warning system, and the concept is built over the cardiac healthcare data analysis. So the thing is that nowadays we are having a lot of problems related to the cardiac health. we have the pre-ejection period, as well as some other issues which appears only intermittently. And for that reason, we are unable to capture the actual behavior of the heart in the real-time manner. So therefore, if we can design a system which can give us the warnings before the eventualities will occur, so it will help us to take the precautionary measures. So the thing is that the conventional methods are quite difficult and unable to judge the future anomalies. And therefore, we are going to use the machine learning to design the early warning system. So this research was carried out during my PhD in the Chanling University, Taiwan. So our lab is artificial intelligence and big data computing lab. So therefore, I use this template to give the due credit to my research lab. And end of this session, first of all, I will introduce the topic that why the things are happening, what the things are happening in the current scenario, especially in the heart functioning. What is my motivation and what are my goals for going for the cardiac healthcare data analysis, followed by the system model that we have developed and designed during the our research days in the PhD. And then after the core idea of the ECG and SCG annotation. So I will let you know about this acronym of ECG and SCG and what are the difference between them. And then after, followed by these two approaches of the without machine learning, what will be the case, and with machine learning, what will the case. So these two main areas I have targeted and have designed the slides in such a way that we will stick to the main topic rather than going here and there. And followed by the results that we have obtained after introducing our idea for the cardiac healthcare data analysis. So this will be the broad outline of the session. So let's start with the introduction. So as we all know that a human heart is a very complex thing where the several valves and the ventricles are working in a simultaneous fashion so that it pumps the blood into the heart as well as it supplies the blood with the oxygen to all over the body to keep them function. But the thing is that nowadays we are having a very different lifestyle compared to like a 40 to 50 years before. Nowadays our lifestyle is quite different. We used to wake up till 11 o'clock in the morning, sometimes 10 o'clock. And there are situations where we need to work overnight, like 2 a.m., 3 a.m. So our sleeping pattern has changed quite a lot, as well as our food habits are also not consistent. We used to eat 3 times a day, sometimes 4 times a day, 5 times a day, and sometimes we eat a lot of food at one instance, and on another instance we hardly eat something. So this kind of food habits, sleeping patterns, and the work schedule, there is a quite a different way we are working now. So our work-life balance is also disturbed quite a lot. And therefore, according to this American Heart Association, has observed that there is a 30% annual mortality rate due to this coronary heart diseases alone in the Canada and the USA. So broadly, this survey was conducted limited to this Canada and USA, but the situation is quite not different in the context also, because in India also nowadays the uh, our millennial people are working in a very different way. They want to eat the McDonald's burgers and Domino's pizza. So our food habits have quite a lot changed. So what happened in this situation is that the heart has a efficient functionality. However, if there is a burden, overburden on our heart, then it will not function as per our expectation. So if you can see, there is a picture of the normal artery is given where the blood is passing through. So under that situation, we will be having a normal lifestyle. We can have healthy lifestyle. However, if our food habit and the sleeping pattern is not appropriate, then there is a slight accumulation like you that appears inside this artery, or we can say the core artery. And what will happen in this case? It try to obstruct the flow of the blood. So we can say on the next image, because the artery is a bit narrowed. So the yellow part in this artery is considered as a plaque. Plaque is nothing but we can say the fat, or we can say the cholesterol, the part of the cholesterol which is not dissolvable. So therefore, it appears inside the wall of the artery, and gradually it narrows down, and the blood of the flow supplies the blood flow is disturbed, where we started feeling the mild pain. So this mild pain will not be consistent. I mean, you feel it for sometimes like 5 to 10 seconds, and then after you feel it normal, and then after 2 3 days, or after 1 week, or maybe the 1 month later, you will again in your heart, on your chest of the body. That will be again for the 5 to 10 seconds if the artery is bit narrowed. But the thing is that if we continue with the current lifestyle, then the plaque will gradually accumulate a lot, and it will appear at some times that it will completely block the artery. So if you can see, if the artery is completely blocked, then in that case, there is no way the blood supplies through the artery. That means the heart is usually supplies the fresh blood with the oxygen to the rest of the body, and then after that blood like accumulates the, like we can say the after the blood is supplied to the different parts of the body, and that unfresh blood, we can say, come to the heart, where again heart will try to refresh it with the oxygen. But the thing is that when the artery is completely blocked, there is no communication with the flow of the blood to the rest of the body, and at that point we started feeling the severe pain. And that we call as a, we have to design a system which can give us the early warning. So here the idea is to, when you start feeling the mild pain, at that time, if your algorithm or the idea gives started giving the early warning that in future, in the, after this many months or in this many days, the problem will be very severe. So here we can take the precautionary measures. So that whole idea is built on the concept of this normal to mild pain to the severe pain. Now, let us give you the idea that why the cardiac early warning system is needed. So we start with this, let us say in the normal state. We consider that a person is in a normal state. And at some point of time, because age or some cholesterol accumulation like you, the person has started feeling, let us say, the instantaneous pain. So we call as the instantaneous onset. And the difference between the critical cardiac condition and the onset of pain is usually like of 10 to 15 minutes. So if you attend the medical services within this 10 to 15 minutes, then it is fine that you have a ample opportunity to recover or get the medical attention, and you will be able to sustain. However, if this 10 to 15 minutes, if you pass, then there will be a very difficult situation for the person to survive. And therefore, when we consider into the context of the India, where the medical facility is not ubiquitous. So in the city, like say the Mumbai, Delhi, or like say in the Bhubaneswar, it is considerable that we might get services within the time. But still, 10 to 15 minutes is quite difficult in India also. So forget about the city. If you go to the rural area, there it is not possible to get the medical services even after 2 hours and 3 hours also. So, so that's what the challenging issue, that after the instantaneous onset to get the medical services, the time is very limited. And during that time, we need to get the medical services. However, what will happen if we have the early warnings? So if I am a person and if I started getting the early warnings in my wearable devices or in my cell phone that this meant for you to having a severe pain, let us say the 60% chance is there. And after 1 month, 1 month, it shows me that there is 72% chance that you will be having a severe pain. So if something will notify me on a regular intervals with some possibilities, then I will be very much immediately book an appointment with the doctor and will go for the checkup. And if something suspicious is found, then I will go for the medical attention. So that's what the ultimate motive over here. So we call this as a golden life-saving time. This is the 10 to 15 minutes is considered as a golden life-saving time. So I have picturized the benefits of having the early warning system. So by this chart, so here in the x-axis, you can see the x-axis represent the time and the benefit of the early warnings, and the y-axis indicates the health. So let's say you have very good health, okay, and as the time pass by, your health is degrading, okay. So you started having some initially a good health, but you started eating a lot of junk food, fast food, the sleeping pattern has changed, so your health started degrading and deteriorating, and at some point of time, this red dot indicates that the disease appear. So there, from there, it is, let's say, the benefits of the early warning is not seen over here. But if you can see this pink dot, we can see the time of the early warning. So over here, let us say I have provided the first instance of the early warning. So at that point of time, if the person gets the medical attention, then you can see that the benefit of the early warning is quite a lot. And you can see the disease without the early warning is quite early compared to the disease point with the early warning is quite farther in the x-axis, the time duration. However, let us say we didn't care much when the first early warning appears, and we continue with the lifestyle of the junk food and the sleeping pattern. So at the second point, let us say we provide the warning, and at that time, the person has consulted the doctor and the medical attention has been provided. So again, the benefit is the relative benefit is not that much compared to the first early warning, but somehow it is better than the without early warning system. So this is the way we can understand that what is the benefit of the early warning system. And different existing cardiac technologies that we can use for the cardiac healthcare analysis. So you can see that there are different ways you can monitor the cardiac function. The first one on the top is like echocardiography, where you can see that there is a monitor and the doctor use the device to monitor the heart functions. And if there is a plaque and other things, then the person can easily, doctor can easily identify the heart functions limitation. The another is a CT scan. So nowadays this terminology is very famous due to this coronavirus. We used to hear that if the person is suspected to be a corona positive, so we go for the rapid antigen test, which is not quite reliable, but the CT scan is quite reliable. So they go for the CT scan. So CT scan is also used for this cardiac function monitoring, as well as this magnetic resonance imaging, as well as the nuclear myocardial perfusion. Now, there are a lot of modalities are available. We can say the technologies are available for the cardiac healthcare monitoring. However, you can see that in each and every technology, the person has to physically visit the center where this kind of uh, imaging or the analysis can be done. Echocardiography, a person has to go to the hospital and they have to take the appointment of the doctor, when the doctor will conduct this echocardiography, and then after you will get the report. So first of all, that your activities of the daily life is highly affected. So if I'm a person, let us say working in some institution, then I have to take a day off from my work schedule. I have to go to the hospital, so it will take some time as well as some efforts and money. So similarly, the computerized tomography scan also, there are centers to conduct the CT scan, MRI, and this nuclear myocardial perfusion. Another thing is that in addition to affecting the activities of daily life, there is a problem that it is expensive. It takes like say $1,000 or $2,000 per person to go for the particular scan, because in addition to that there is a charges for patient. So another thing is that what we have to do, you will be confined to a room area. And the third thing is that the cardiac problems are not continuous. As I already mentioned, that if you feel a pain over here for 5 to 10 seconds, then it is not necessary that the pain will continue for the next 30 minutes or next 1 hour. So 5 to 10 minutes of the 5 to 10 seconds of the pain, maximum 20 seconds or 30 seconds. Then after sometimes you will feel relaxed, and then the next pain appears after 2 days, 3 days, 5 days, a week. So these modalities or these technologies having a limitation that at the time of the pain, if you visit the doctor and the scan is performed, then it will be accurate. It will give you the accurate results. However, when you feel the normal and you don't feel any pain, and at that time the test is conducted, then very less chance that sometimes of like the problems will be identified. So those are the limitations of these existing modalities. And therefore, what we need to do, give me a time. Okay. So what we can done, what we can do is that we have to use some technologies which can identify the pain when it appears intermittently, and it continuously monitor the our heart functioning. So as I told you that the cardiac irregularities appear only intermittently, and in many instances, the mild cardiac irregularities go completely unnoticed. But at the same time, they have these serious consequences. So we have this ECG, you can say the electrocardiogram. So nowadays, ECG is quite handy with the help of this technology. So what we used to do is that there are some wearable devices also nowadays in the market. But before those wearable devices commercialized, there were some in-house or in-laboratory experiments using the sensor devices. So what they usually do, they put the sensors on some selected areas, on the specific areas of the chest, and they try to connect with the Bluetooth or some wireless technologies to retrieve those signals. And once those signals are retrieved, they try to analyze the irregularities. So as I have told you before, you can see that there is a person, and this is a, like say, the ECG signal of that person. So you can see that there is some normal ECG cycles before that, and then after there is a sudden pain. We can say it's an intermittent abnormalities, and after a few seconds again the person started feeling better. So the ECG is completely normal. Now you can see that you suppose you visited a hospital during this normal ECG cycles. So the doctor will definitely say that you are healthy, you no need to worry for your heart, and you can continue with your lifestyle with some precautions. But you can see when after the person came out of the hospital, reached to the home, intermittent abnormalities appear. So these kind of situations are quite difficult to manage, and therefore the people have started designing this body area network. So what they usually do during this body area network is that they put the sensors on the part of the body, selected body area. So you can put over here also. You can put at the chest area. So there are some selected locations where you can put the sensors to acquire the ECG signal. So once those ECG signals are acquired, either you can transfer them to the cell phone, because that is quite if the sensors can transmit some signals and you can collect those signals into your cell phone, then the cell phone is always connected with the internet. It is quite normal nowadays that the cell phones are connected to the internet. So once the signals are available into the cell phone, you can transmit them via internet to health analytics platform, where the signals will be continuously analyzed. So imagine a situation that in this area of the Bhubaneswar, there is a product which can collect the signals via cell phone and transfer them to the health analytics platform, which is cloud connected. And there are, let us say, 100,000 person, 1 lakh. So this cloud data centers can continuously monitor those 100,000 people and can keep the records of those data and correlate them with the other, so that they can identify in the real-time manner that which person is healthy and which person is having the chances of getting the abnormalities. So that is what the idea. Now there are different type of the cardiac data. So we can see the different modalities can have a different function, and based on that we get the different types of the cardiac data. So the first of them is the time series cardiac signals. That means as the time goes by, the signals will appear in a different way, or we can say the different pulses will appear. So the quite obvious um, cardiac data under this time series is the electrocardiogram. We can say the ECG. We all know about the ECG, so there is a very little to discuss over here. However, the another type of the data is a seismocardiogram, which we call that as SCG also. So the seismocardiogram we can understand with the help of the seismic activity. So the earthquake, we can say, how do we measure the intensity of the earthquakes? So because we have certain types of the scales available, or we can say the sensors, which can measure the vibrations of the earth. So if the vibrations are quite a lot, then they capture that it's a 6.7 magnitude earthquake. So these seismic activities, or we can say the vibrations, are captured by certain types of sensors. And when those sensors are used on the chest area, they can also capture the vibrations which are induced by the heart functions. So therefore, those signals retrieved due to the vibrations are called as a seismocardiogram. So this is another technique to understand how the heart is functioning. And the third thing is balistocardiogram. So that ballistocardiogram is also similar to the seismocardiogram, and it captures the heart vibrations. But the thing is that they are using the different type of the sensor. So therefore the data is also a bit different. Then another is the imaginary cardiac data. So all those like the CT scan, this magnetic resonance imaging, myocardial perfusion imaging, and the chest radiography. All these are the image based. So everybody has seen this X-ray. So X-ray is nothing but an image of a that is an image when you perform this chest radiography. So you will have this some different parts of the heart will be visible. So mostly they are used to identify the blockages inside this arteries. And the another is that the another third type of the data is a visual cardiac data. So those are the imaginary cardiac data, but when transformed into the using the into the DICOM format, they become the visual cardiac data. So those are these computerized tomography scan, again CT scan and DICOM format, and the magnetic resonance imaging in the DICOM format. So now let us go back to the electrocardiogram. Let me introduce the electrocardiogram because we are trying to build our machine learning model on the ECG and the SCG signals. So therefore, it is quite necessary for us to understand the functioning of the ECG, the cardiac electrical activities. So on the left hand side, I have put a graphical image which can see that how the cardiac electrical signal is passes across the chambers of the heart, and based on that activity you can see the ECG signal has been generated on the top in the blue color. So that is a typical ECG signals. Now when these ECG signals appear, there are different things which goes inside this heart. first of all, you can see that from here, you can see that a spark is generated, and that spark is transferred to the rest of the heart in the form of the electrical signal. So that is because of this SA node, which generate that spark. So you can see the starting of this yellow color over here, which is considered as the arterial depolarization. And for that reason, this P wave in the ECG will be generated. Now you can see when that signal reach to the appears over the heart, then again it will start replicating or back to the node where we can see the ventricle depolarization will start appearing. And for that reason, this R, we can see the R or we can see the QRS waveform will be generated. And then you can see that was the arterial depolarization, ventricle depolarization. Then after the ventricle repolarization will occur. So with that reason, the T wave will appear. So there are three types of the things will appear: arterial depolarization, ventricle depolarization, and ventricle repolarization. And this complete ECG wave will comprise of 5 feature points, we can say in our computer science terminology. We can say P, Q, R, S, and T. Now, the thing is that when you go with the early warning design system, you need to continuously monitor the signals. We can see the P wave. First of all, you can see the P wave. Then you have to monitor this QRS wave. And then thirdly, you have to monitor the T wave. So any distortion P, QRS, and the T wave possibly lead or give us the indication that there is something unusual happening with the cardiac electrical activities. And for that reason, we have to first of all identify this P, Q, R, S, and T, which we call as a annotation of the ECG signal. So I have to annotate, let us say I have to annotate this particular waveform. So I don't know, like if I'm not a cardiac expert, then I don't know which wave this particular peak will indicate. Either it can be a P wave or it can be a T wave. But if you are a cardiac expert, then you will definitely say this is a P wave. Okay, so this will might be a T wave, something like that. So if I'm not an expert, you might be saying that this might be the QRS wave also. So over here it will be a P wave. So that is a challenging issue when we come to the annotation. So for analysis, the first challenging issue is for the annotation. So you can see we are casually coming from the broader research problem to the very specific research problem of the annotation. So once you do the successful annotation, then you can do the different types of measurements. We can say the cardiac time intervals. We will discuss them in the upcoming slide also. So this is the ECG signal. Similarly, we have the SCG signals. Now, why we want to discuss the SCG when we have already the ECG signals available? The thing is that ECG signals is generated due to the electrical activities only. And there are very limited number of feature points. There are only 5 feature points, which I already told you that the P, Q, R, S, and T. So with the limited number of feature points, we can have a limited data analysis. But if I wanted to know the clinical activities of the heart, then I need some different perspective or different look at the heart. And that can be achieved with the help of the seismocardiogram. So you can see here, you can easily see the openings and closing of the valves. So here you can see the aortic valve. This is the mitral valve. So when the valve will open, the blood will fill the ventricles. Then there will be a depolarization. Then the blood will goes out of the valve. So for each particular process, like to fill the ventricles and to empty the ventricles, we need to see the movements of the valve when they open, when they close. And the ventricle will also be able to depolarize properly so that the whatever blood it has accumulated that can also pass back to the another chamber. So the movement of the ventricles as well as the opening and closing of the valves are the essential components to understand the function of the heart. And therefore, this ECG signals cannot give us this information. And for that reason, we are going with the seismocardiogram signal, which we call as the cardiac mechanical activities. So the typical signals of the cardiac mechanical activity has been shown over here. So let us go back to understand that what will happen and what are these peaks, different peaks are telling us about the underlying cardiac mechanical activities. So I have, for your information, I have put some different terminologies that what AS indicates. So compared to the ECG, the SCG has the well-defined 9 peaks. So those peaks are the AS, which stands for the arterial systole, then the MC, which is called as the closing of the mitral valve. On the top, you can see there is a point to the mitral valve. So the opening and closing of the mitral valve. So MC indicates the closing of the mitral valve, and this MO over here will indicate the opening of the mitral valve. So all these pictures indicate some different cardiac activities in the seismocardiogram. And again, if we can successfully annotate the peak, then it will help us to know that when this aortic valve will open. So this AO is aortic valve opening. So if I successfully annotate this peak, then in the heart signals, or we can say the monitoring, we can see when the AO is appearing proper time or not. If the AO is not appearing at the appropriate time or expected time, then there is some problem in opening of the aortic valve. Similarly, in the opening of the mitral valve. So if there is some problem in this mitral valve, if it unable to open or if it unable to close at the expect as per we can see and go to the signal and try to monitor this MO. You can say the opening of the mitral valve. So therefore, there are the different feature points available and annotation is required. Now let's come to the motivation that we have the ECG and then after SCG. But ECG, we can say that so far when the sensor technology has evolved, prominently the ECG signals were used because it was considered as a golden standard for the real-time cardiac monitoring. So what the usual frameworks we have seen is that the sensors are attached, the signals are retrieved, and they go for the annotation of the ECG. And after the annotation, they will measure this RR interval duration, a QRS duration, the height of this R, and the T wave duration, etc., to identify the different anomalies in the activities. However, we can say the ECG is not completely reliable as per the literature because even if you have some cardiac mechanical problems, then it will not appear in the cardiac electrical activities. So both are quite different perspective to look at the heart functioning. You can see, I just go back to the previous slide to see that the cardiac mechanical activity where the mechanical functions are prominent, but in the cardiac electrical activity, it is all about the electrical wave transmission across the heart. So they are they are used to complement each other rather than we can omit any one of them. So therefore, the ECG is not completely reliable because it doesn't reflect the any of the mechanical activities. And due to the limited number of the features, there are only 5 features are that P, Q, R, S, and T. So it provides very little insight in the form of the signals. And therefore, for the improved monitoring, we need to have the deeper insights of the cardiac activities, which we can accomplish using the other time series cardiac data. In this case, we have analyzed the seismocardiogram data. So why we go for the seismocardiogram? Because it offers the cardiac mechanical insights such as valves opening and closing, then the blood flow rate, then the ventricle contractions and expansion. So you can see these 3 things which I have already mentioned, that all the 3 things appear prominently in the SCG. We go back previously to this. You can see this. You can see the blood flow rate. So at what rate the ventricles are filled with the blood. So that is one of the activities. At what rate the valves are opening and the closing. The third thing is that at what rate the contract as well as expand. So at the time of the contraction, the chambers, the blood goes out to the chamber, and at the time of the expansion, the bloods are filled into the ventricles. So these are the different mechanical activities which you can easily identify from the seismocardiogram. You can see there are different annotation points over here. So the foremost benefit it will bring into the analysis is that they can also be captured using the low cost accelerometer sensors. So similarly to the ECG, we no need to go for the very high end device. We just put the accelerometer sensors again onto the surface of the chest area, and we can retrieve these SCG signals. And the another thing is that it does not compromise with our need of the continuous monitoring. So with ECG, we can continuously retrieve the signals and go for the monitoring. So by addition of the another technology, we can say seismocardiogram, we still can continuously monitor the heart functioning. So suppose somebody has designed a smart jacket where some sensors are accelerometer sensors are put over the appropriate place in the jacket, and I use that jacket. So now what will happen from the chest area, the sensor will acquire the signals and that will be passed to the cell phone for further processing to the cloud data center. So the thing is that it brings some more insights. At the same time, it doesn't compromise with the existing mechanism. So that's what the benefit of the seismocardiogram. And this has motivated us to go for the seismocardiogram analysis. Now we can also some go for some objective analysis also, because that is also important. If you just say that seismocardiogram is useful and it is inexpensive, that doesn't make any sense. But we have to go for the different aspects to confirm that the seismocardiogram will help in addition to having the ECG signals. So we have compared these different cardiac health monitoring techniques like the echocardiogram, CT scan, MRI, MPI, ECG, and SCG across the different aspects. So like whether this is expensive, can it be used for the continuous monitoring, whether it is easy to acquire the signals or the details using the technology, and do we need some expertise to carry out the signal acquisition, or the what when we acquire particular data on the cardiac health, are those data quite reliable or not, whether this particular technology has been well studied or not. So wherever we have different aspects, so we can see in the terms of the echocardiography. So they are expensive, but they cannot be used for the continuous monitoring, and they are not easy to acquire. In addition, we need some expert, that's a doctor, to carry out the echocardiography, but at the same time, it is reliable. So it doesn't fulfill our two requirements like the continuous monitoring, and it requires the experts. So it doesn't make any sense to use the echocardiography. Similarly, the CT scan, MRI, and MPI, all those cannot be used for the continuous monitoring, and all of them require some experts. So therefore, we need to identify those which are helpful for the continuous monitoring as well as doesn't require the expert person. So similarly, we can say the for the ECG, we can use low electrodes, and for the case of the SCG, we can use the low cost accelerometer sensors. So if you want to relate this sensor, you can have this cell phone device when there is accelerometer sensors are already installed or already embedded. So you might download some app which can count your steps. Like today you have walk for 500 steps, 5,000 steps. So how do they measure that how many steps you have taken in a day? So those apps try to read the accelerometer's reading, those sensors which can identify the movements. So if you are at this particular position and if you change the cell phone device to the next place, then it will count the distance. It will measure the distance using the accelerometer. And from that, they try to judge that how many steps you taken. So the same accelerometer sensors we can use out of the wearable devices for the continuous monitoring. And this both the technologies, ECG and SCG, they will complement to each other for the health analysis. So ECG, if you are using only ECG, then they are inefficient. If you use only SCG, they are also, it is inefficient. But when you combine them, they can give the different information. You fuse those information and get the efficient monitoring. So what should be my goal? I have identified the problem. I have identified the technology which should be used for the given purpose. Now what to do when I have both the technologies available? What should be my goal? So my goal is to annotate the signals. So I can annotate the ECG signals as well as the SCG signals. And there are two ways. Either you use the approach or you can go for the machine learning based approach. So I will discuss this, why the conventional approach are not sufficient and what the need of these machine learning approaches. So this is what my ultimate goal. If I annotate the feature point, then I can do anything. I can measure the time intervals also. So let us discuss about the system model. So the system model can be easily understood in this way. Uh, this was the system models we have designed during our lab experiment during the PhD. So we have designed a body area network. The nitty-gritty of this body area network cannot be discussed due to the time limitation. But the broadly, what this body area network has, there are the wearable devices components. So we have the data acquisition modules, we have the data communication modules, and we have the early. So if I want to relate with the analogy, so this data acquisition module can be understood as any of the wearable devices. So there are smart jackets, there are smart t-shirts, smart belts are available, which you can use at the chest area with the help of these electrodes and sensors, which will acquire the signals. So that's why it is a data acquisition module. Then the data communication module. So either you can use your cell phone. So when the data acquired by the sensors, you can get them into the smart devices, either your smartwatch, smartphone, smart glasses. And from that, those smart devices are connected with the internet. So they communicate with the health platform. So once the data are available at the health analytic platform, there will be the algorithms will run in the background, continuously monitor the signals. And whenever some abnormalities will appear, they will give the signals to the early warning module, which is designated as a rectangle. So there can be a different types of the way you can intimate the person. So we have broadly classified them into this like normal, mild, and severe. So you can understood this normal there. So at any point of the time when you open the app, and if there is a green signal, that means the data are continuously passed to the cloud platforms where it has been already analyzed and the outcome is normal. But suppose at some morning, if you wake up and open the app where the signal is mild, so it indicates lots of abnormalities, or we can say the mild abnormalities are appearing intermittently, and it's a time to have appointment with the doctor to consult. So that's what the broad idea of the system model. And based on that, since that was the broader aspect, but in the laboratory experiments, we have designed this system model in a way which help us to acquire the data. So what we put, there are 4 accelerometer sensors we use at the 4 different locations. So this AV indicates the aortic valve, MV indicates the mitral valve. Similarly, we have 4 valves. So we use the 4 accelerometer sensors on the body area, which help us to acquire the SCG signals. Now, similarly, we have used the electrodes. Over here, you can see that we have used the electrodes at the uh, both the hands near palm as well as on the left foot. And from there, we have acquired the ECG signals. And now, both the signals are in an analog form. But if you want to analyze them using the MATLAB or some software, you need to digitize those analog signals. Ultimately, you have to bring them into the form of the numbers. So therefore, we use this analog to digital circuits where the signals are digitized based on the sampling rate. So that is what the SCG. Here ECG also at the same time transform into the digitized format where we use this synchronized data logger. So both the signals are acquiring the same pulse. That if the one times the beating was done, for that heartbeat we have acquired the SCG signals. For the same heartbeat we have acquired the ECG signals. So only the aspect is different, but it contains the same heartbeat. So we lock them the data into this synchronous logger and transfer them into the analytics platform for the combined ECG and SCG analysis. So that's what the in-laboratory experiments we have conducted to acquire the data. And for more details on this analog to digital conversion of the signals, so what will happen? So you can see on the top, there is a typical ECG signals that we have acquired in an analog format. And once that signal has been passed through this ADC circuit, we have used this sampling rate, let us say 400 Hertz. That means in a 1 second, whatever the signal we have acquired, it has been sampled 400 times in a second. So there will be a 400 data points. You can see the compared to the left picture of the analog, the right one is a digitized with the dots. This indicates the one sample. So there are 400 samples in a second. So if ECG pulse duration is for 1 second, then each pulse, let us say, will be having the 400 samples, which will ultimately depict the same analog signals. Now, in the terms of this analysis, what we can do when we have this set of the data points, we can fuse them or we can use represent them into the form of the vector. So let us designate that as a vector for the ECG. We call it the VECG, which represents the digitized ECG form. Similarly, we have the another vector for the SCG, which is which represents the SCG signals. So this is just for the understanding part, but in the bottom figure you can see we have used 4 accelerometers, like if you can see the signals here. We have used here 4 sensors on the chest area. So each sensor has acquired its own unique signal. So this signal was for the TV, but here we have acquired the SCG for the mitral, then tricuspid, for the aortic valve, and for the pulmonary. So there are 4 SCG signals in addition to 1 ECG signal. And when we digitize these signals, this is for the visual platform, but when we digitize them, it will appear in the file format. It can be a text format, .csv format, anything depending on your implementation. So here it indicates in the form of the text file, CSV file, but it has opened the text format. So the first indicates the time, then the ECG signal, then there are the 4 different SCG waves for the mitral, tricuspid, aortic, and pulmonary. So now we have the data. The first thing before we go to the analysis for the acquisition of the data. So that we have already acquired into the file. Now we jump into the analysis, that how to analyze the data. So what should be my target over here to know whether the cycle is normal or abnormal? So I need to first of all consider the ground truth from the healthy individuals, because if you take the signals from the unhealthy person, then you won't be able to establish the ground truth. So for that, Let us consider that this is a ECG signal. And for our understanding, the ECG signal is annotated as a P wave, QRS, then T, and then the cycle repeats. So what I will do, there are different things in a single ECG cycles. There can be some intervals and there can be some segments also, and each and every aspect is important. So let us say we have a signal and there are three waves, like the P wave, QRS wave, and the T wave. So this is we can say the P wave, then the QRS wave, then the T wave, and then for the next half cycle, again the things will repeat. I have represent them with the X. So X belongs to this P, QRS, and T. So for a common terminology, I have represented XWV, which represents the particular wave, and that X belongs to this set P, QRS, and T. Similarly, there are some intervals also, which we call as a PR interval. So PR interval means that there is a R peak, there is a P peak, and the distance P wave and the R is called as a PR interval. Then there is some QT interval, and there is some RR interval. So from R peak to R peak, there is an interval we call it the RR interval. And similarly, we have the segments. So segments are only two. One is the PR segment and ST segment. So the PR segment is from the offset of P to the end onset of R, which we call as a PR segment. And there is a ST segment that is from offset of S to the onset of T. So this is called as a ST segment. So this is the way you can first of all understand the existing thing. So we have three waves, three intervals, and two segments. Fine. Now we have to first of all acquire all the signals from all the healthy individuals and try to identify the range for the waves and the segments. So that we can do for acquiring the health signals from the healthy individuals. And based on that, once we successfully do the analysis, we can identify the pre-ejection period, left ventricle ejection time, and the electromechanical systole. Now, these three are the cardiac time intervals which cannot be obtained solely based on the ECG. So we have obtained all the information from the ECG. Now we correlate them with the SCG. So usually the pre-ejection period is the onset of the R waves up to the AO waves. So that will call as a pre-ejection period. If there is a variation in this cardiac time interval, there is some abnormality. Similarly, the left ventricle ejection time is the period from the AO till the offset of T, we can say, so AC. So that is what the left ventricle ejection time. So that is another cardiac parameter that we need to analyze. And now we go for this annotation process without the machine learning. So far we have understood that what are the things required. This much information we can obtain if we successfully annotate P, QRS, and T. So therefore, it is quite essential for us to annotate this ECG signal. And therefore, we come over here. First of all, we start with the without machine learning. Okay, so we start, let us say this ECG signal has been acquired. There is a cardiac cycle 1, then there is a followed by cardiac cycle 2, and no point has been annotated initially. It is completely blank. So how we can start the annotation process? First of all, try to acquire the ECG R point. So for a person like me, I have studied this ECG signal. I can know that this is the R point. I can visually see that. That is the peak with the highest amplitude. The peak with the maximum amplitude. It is a quite distinguished point in the entire ECG signal. So you try to first of all get the R point because it's quite easy point. What you need to do that you have to apply the max function into this entire data points which you have digitized. When you apply the max point, you will definitely get this peak, which is at the maximum amplitude. So that you annotate as a R. Again, for the next cardiac cycle, apply the max function. You will definitely get this peak. It is quite intuitive to apply for this. So you will get the another R peak. So R point annotation is quite easy and can be accomplished very using the max function. So once the R is, what you can do with respect to this R point annotation, you have to annotate P, Q, S, and T annotation. So what you can do for the annotation of the P point, now let's say the R is our reference and you know the duration of this PR segment. PR segment is from the offset of P to the onset of R. And you also know the wave duration of the P. So that we have already established of the ground truth from the healthy individuals. So with using this PR segment and the P wave duration, what I will do, I will go for the sliding window. So I will find the maximum point in a window with the reference point R and the time duration before the P wave. So in that duration, I will try to apply the max function, which will find us this max peak, which we will annotate as a peak P. Similarly, for the Q function, what you can do, for the PR segment, you will apply the mean function. So PR function, that means from here to here, you will apply the mean function. Similarly, from R to T, like from the onset of T to the offset of R. In between, when you apply the mean function, you will get the S wave. Similarly, for the T wave. So this is the way you can go for the annotation without having a machine learning. So what we can do in the terms of the software, this is for our understanding the visual purpose, but we don't have the signals. Ultimately, we have the vector of the data points, which we have represented using the vector of ECG. So let us say we have this vector of ECG, all are in the form of the dots. These are the continuous signals. Then we first of all find the maximum amplitude point. Let us designate it as a point over here. So these are all the points. And then find, now what we are going to do over here is that for each signal, we have to find the maximum point. Over here, the find maximum point. So we find the maximum point for each ECG signal, ECG cycle. And then what we are going to do is that, which are the other possible R points? So all the vector points in the ECG, which are having the amplitude greater than or equal to this point, are considered as a potential, or we can say the candidate R points. So these are just the candidate R points, not are the actual R points. We need to confirm whether the candidate R points will become the R points or not. So here, first of all, we need to identify the sigma R point, which we have experimentally obtained. So here you can see that the vector of the ECG point should be greater than or equal to sigma R point. So this sigma R point is a bit difficult to obtain, but if you have the acquire the signals from the healthy individuals and perform the analysis, so here we have gone for this receiver operating curve, ROC curve analysis for this sigma R point. So we have taken the different values for them, like so 0.7, 0.8, 0.9, 0.6. And accordingly, we try to estimate the benefit which accrued out of the analysis. So for only the point, that is the points like the sigma R point, which is 0.7, at that point of time, we have the better outcome compared to the 0.8, 0.9, and for this sigma R point is very critical to decide, and you need to decide it experimentally only. And once you have this candidate R points, then from that, which using this VECG as a vector, and this candidate R points, you apply this max function, and you will definitely get the R point. So this is the way you can go for the R point analysis. It is quite similar that we have understood in the with the concern of the signal, but experimentally you have to decide the sigma R point. So that's for the R point analysis. And now we have 3 waves, 3 intervals, and 2 segments. So for those, we have to first of all obtain the reference feature values. So what those reference feature values are? Those reference values that we have obtained from the subjects. So let us say we obtain the delta x wv. So all those wave duration can be represented as a x wave. So we have two things like the maximum possible wave duration and the minimum possible wave duration, because each healthy individual is different and the wave duration may change from one person to another. So what we can take that from minimum to the maximum range we can take, and we can designate them as a delta x point and the delta small delta x wave. Similarly, we go for the interval, segment, as well as for the amplitude, where this x belongs to this p, qrs, and t. Similarly, this y belongs to this rr, pr, and qt. And z is segment. So we have only 2 segments. So this pr and the st. So that reference we obtain from the healthy individuals. Once you have this information is available, we go for the annotation of the other points. So from here, we have this ECG R point annotation already done using the previous method. Now we go with the other points annotation. So first of all, let us say calculate the range for P. So this is indicated as a range for P, that is the onset of P to onset of the R. So this is the range of the P. Again, calculate the range for Q. Again, for the onset of Q to the R, for the S, and for the T wave. So first of all, we need to identify the range for each and every feature points, and in each feature points, depending on the maximum and minimum, we will apply the function. So for the P point is at the max, so we apply the function over there. For the Q, it is a minimum in that particular range. The S is also the minimum, so we apply the minimum over here function, and this T is the max function, so we apply the is the maximum point, so we apply the max function. And then what we are supposed to do is that you can see that the Q range, so where this Q particular appears, it appears before the R point. So what we are supposed to do is that whatever the position of the R point, we need to subtract something, because we are going into the reverse direction. What we are subtracting? We are subtracting the wave duration of the QRS. So this QRS is having a wave duration that we subtract. So the QRS is the entire, you can see the QRS will appear over here. But with respect to R, it is just half of them. So that's why by 2. So from R minus something point up to R, whatever is there, the distance we call as a Q range, and there we apply the minimum function to get this Q point. Similarly, we can have this S range, P range, and the T range. So for S and T, we can see that there is the R point plus. For the T also that appears after the R, so that is R plus. However, for the Q and P, it is R minus always. So that's what the formulation you can derive. And then after you find the max and mean, and accordingly annotate the rest of the points. Now for the SCG annotation also without this machine learning, first of all, we identify the AO point. Now this the concept will follow. So I'm not going to discuss much in detail because we have the machine learning approach also. So this AO point will appear over here. So AO is quite distinguished compared to the rest of the points in terms of the amplitude. So Similar to the R points, you can obtain this AO points easily. So this AO point annotation is first step. The second step is the annotation of the rest of the points. So now I go quickly because the concept is already well understood. So first of all, we get the vector of SCG. We find the max point, that is what we can say amplitude in the entire signal. With respect to that, we have to find the delta AO point for the potential candidate AO points. So now you can see that there are two potential candidates over here. Either this one can be AO or the second one can be AO. So now the confusion is a bit more in the terms of the AO, and that's why the experimental analysis of this receiver operating curve. In the ECG, it was not quite obvious that why we are going for this experimental analysis of the sigma R point. But here you can easily understand that why we need a sigma AO point analysis. So we have again performed the experiment and we found that the sigma AO point should be 0.75, which can probably give us the better result during the experiment. So with respect to that, we have identified all the candidate points, and among that, whichever is the maximum, which we consider only the AO. So you can see there are multiple points available, but the one which is the maximum will only be considered as the AO. So here there are two candidate points. So the one only will remain. Similarly, from the last three signals, there are two candidates, but only the one with maximum will be retained. So this way you can first of all annotate the AO. And now after the AO point annotation, again we calculate the range for AS, IM, and all the points up to the RF. There are 9 points in the seismocardiogram. And depending on the maxima and minima, we try to apply the function. So for the AS, we apply the max function. For the IM, we apply the mean function. And for the RF, we apply again the max function. So successful application of the functions will label the specific peak as an annotation point. So that's what the SCG point annotation without the machine learning. So this is the normal SCG cycles of the healthy individuals as the data has been obtained from the actual human heart, and we have successfully annotated this AO point. And this is the range for the AC. So we can have a window protocol for the AC. Now, why this particular point of the AC is important? If you can go back over here, you can see the AC point is quite farther compared to this AO. It is quite at the distance. And similar to the ECG, the AO here in the SCG is our reference point. So from AO, we need to find a range for the AC point. Now you can see the difficulty is that the AC will appear in a very small distance. Okay, the gap, or we can say the window size is quite small. So with respect to AO, if you take, so this is a sliding window for AC on-site as well as for the AC offsite. So with that margin, like compared to the ECG, SCG is a bit difficult due to this reason, because the signals are quite difficult to analyze, as well as the number of peaks are more compared to the ECG. You have the sliding window for the AC, and then you have to take the alpha judgment, or this parameter also need to be experimentally obtained. So the sliding window for the AC plus or minus the alpha judgment you have to take in order to get the range for the AC. And this error margin you need to obtain experimentally, and then after you apply the max function on the AC. Now we go quickly to the annotation of the SCG using the machine learning. So we have limited times, but I'm trying to give the main heart of the topic of this cardiac healthcare analysis for the machine learning. So here for the SCG annotation using machine learning, what we have designed is the framework that how we will go for the annotation first of all. So there are 3 phases. We have divided the entire process. One is the training phase, pre-processing phase, and the testing phase, and final pick selection. Now, this is not conventional training testing phase because we are dealing with the signals over here. So, first of all, let us understand what the things are happening in the training phase. So, first of all, you have to obtain the feature rules, or we can say the features. Simply, let us say the features. And we have the machine learning models. Now, we use the annotated training SC cycles, that means the ground truth. So, me and my colleagues and others uh, spend a week over these 9,000 SCG cycles, and we have manually annotated each and every point to generate the ground truth. So we use these annotated SCG cycles, and we use the features and the machine learning models to learn the feature values as well as to train. So that was the training phase. Now, when we apply the unknown cycle without any annotation, we want to annotate a signal. So what we need to do, first of all, we need to pre-process the entire cycle. So let us say we have this input, which we call as a test, ECG, and the SC cycles. So we have designed the representative rules to formulate the zones. And within the zones, we have applied the distinctive property to identify the candidate picks, and those candidate picks will be ultimately filtered by this trained machine learning models to retain only the final picks on the SCG or SH. So that was the entire process. The important thing is to understand over here is that how the different phases are working in a manner that will ultimately help us to identify the final picks. So let us come directly to the SCG because ECG is quite simple, so I'm not touching to that part. But the ECG is a bit complex in nature to annotate the 9 points. So you can see we have designed the 3 rules for the feature identification. One we consider as the amplitude. Each and every point has a different amplitude over here. So that can be one of the distinguished feature. Like AO is having the maximum, always maximum amplitude. So with the help of amplitude, we can have some judgment, whether it can be AO, it can be RF, it can be IC. So another feature point is the time of appearance. Like you can see as the time goes by, the features appears. First of all, the AC will appear, then MC, then IM, then AO, then IC. So it is a time dependent points. So the time of appearance can be another feature, and the count. How many upslopes and downslopes the particular feature points is away from this reference point AO can be another indication of the feature. So we use these 3 features. So this is called the feature designing. So that's what we have done over here. Feature extraction is completely different. From the given columns, we identify the important features. But this is entirely feature designing process. So when the features are already available, we go for the zone formation using the representative rules. Now, the thing is that there are several data points in a vector. And if you go and compare each and every data points, then it will be a time consuming process. To speed up the entire process, what we did, we have identified the zones where there is a maximum possibility for a particular point to appear. And that zone formation process we have done in concurrent. So the first feature rule, we can say the representative rule is that we have aligned the ECGP point offset to the QRS onsite with the SCG. And that help us to get the point AS. So you can see that in the zone 1, there is a maximum possibility that you will identify only AS. Similarly, in the zone 2, we have formulated. So in that range only, you have to search for a particular point, which can be MC, IM, IC, and RE. And similarly, we formulate the third zone to identify AC, MO, and RF. So you can see we have significantly reduced the time or the effort of the searching process. Only within that limited zone we will be able to find that point. Then after the zone formation, we go for the candidate identification using the distinctive property. Now each peak is having a different distinctive property. Like for the AS, so AS is always a max peak. You can see the SCG peak over here, the zone is over here, and in that zone, when the max peak appears, then you can have that point AS available. So based on the maxima and the minima feature, we have identified each and every SCG peak and allocated the property to identify the candidate points. And once the candidate points are available, we go for the different machine learning algorithms. So before that, we need to formulate the binary classification problem. So here, what we did is that, let us say for this candidate peak AS, there are 2 points over here. So some particular point can be an AS point or cannot be an AS point. So there are only 2 possibilities for any peak to be selected or the rejected. So therefore, this entire problem we have formulated as a binary classification problem, where any candidate peak will be either selected or can be rejected. So in any zone. So you can use the different binary classifiers like the naive Bayes, support vector machine, logistic regression, and then after you perform the comparisons to know that which algorithm or which machine learning model performs better on a given data. So that's what we have done is the binary classification problem. So to briefly understand this entire process, let me go with some mathematical terms so that we can formulate the machine learning models. So let us say we have these 3 features: when the count, time, and amplitude. So let us say this capital C represents the count, T represents the time, and A represents the amplitude. This X represents the any feature point. So for any feature point, you have any feature point, you have 3 features. For AS, you have the count, time, and amplitude. Similarly, for MC, you have count, time, and appearance. So that is for the candidate peak AS. So we have, let us say, the set of the candidate peaks as of 1 to n. So in the case of AS, we have 2 candidate points. So here the n value can be 2. For the, you can see for the MC, you have 3 candidate points. So you can have the n is equal to 3. So to generalize them, let us say we have the set CPX, which represents the candidate points. And there are only 2 classes, either selected or the rejected. So let us say the C1 is selected, C2 is rejected. So we generalize the term as CK, where K belongs to anything, 1 or 2. And for any candidate pick, let's say CPIX. So for any candidate pick, CPIX belong to CX. We have these 3 features which we represent as FIX. So now apply the naive Bayes algorithm. There's a naive Bayes algorithm. What will it try to estimate is that it try to estimate the probability to be in any class CK given the feature values. So for X, for any feature point X, okay, for any feature point, we have the feature set, these 3 points. So given a feature, what is the probability that will appear into class CK? So that is what we try to expand, that they are like in the naive Bayes, they do not depend onto each other. So we can just individually apply them into the different features. So here you can see that the third expansion, that the probability of CK multiplied by probability of appearing this feature provided the class is CK. So we then appear the probability of appearing this particular count given that the class is selected. Similarly, to have the probability of this particular class provided the class is rejected. So for each of them, we will try to calculate the probability, and then we get the value. So now this probability can be obtained mathematically provided you have this mean value available. And this mean value you can calculate is from the set of the different cycles. So this mean represent from different cycles what will be the average representation. And with the help of that, you get this P CIX given C, P TIX given CK, P AIX given CK. So once you have these values available, you substitute the value. This P CK is nothing the prior probability of the class. So both the class are having the equal representation. So always it's a probability of 0.5. So you have this mean and the variance available. And then when you apply this function, so you have all the values when you substitute and apply the arc maximum function, you will get the final outcome of the class. So that's what you can apply for the, that was the mathematical foundation of the naive Bayes. But in the scikit-learn or wherever you apply this algorithm, you no need to have this understanding to implement. You just simply call the model naive Bayes, and then after the things will be done by the underlying model. So similarly, if you apply this support vector machine, you have to understand the support vector machine. So initially you will assume that the data might be linearly separable, which it cannot be also sometimes. So where you will apply the kernel tricks. So I have just mathematically explained this, how the training samples can be arranged. So this ZX, okay, that's the linearly separable training data, but the data point with the corresponding class is arranged in a form of this set. So Y indicates the actual outcome and ZX indicates the particular point. So again, we have the two classes, and for any candidate pick, we have this feature set available. And then our goal is to find the hyperplane, which can partition the entire set ZX of the different points into two classes, which can be considered as Z for the class selected and for the ZX minus 1 for the class rejected. And then you will apply this support vector machine function, where in addition to this hyperplane, you will also identify the another hyperplane for each class. So that there are two classes, binary classification, there will be two hyperplane in addition to the main hyperplane, which will ensure that there is a sufficient gap, or we can say the distance between the kernel points. So that's what your ultimate goal is, to find the hyperplane ZX. And then we apply this optimized classification hyperplane to find the hyperplane for belongs to that particular class will be considered as rejected, another will be considered as a selected. So this is what the SVM you can apply. And the logistic regression also, you can first of all have the label training data. We have two classes, the binary classes. We have all the candidate features with this feature set FIX, and there will you apply the logistic linear function to identify the points which are either selected or the rejected. So here, this logistic linear function is quite famous, and it is standardized. So you just apply over here. The main thing is to obtain this beta 0, beta 1, and beta 2 and beta 3 function. So those values will be estimated from the training data set. So you simply apply this logistic regression and obtain the outcome. So once you apply the logistic regression, then after you have to go for each point, you have to find the what is the probability that the particular point will be selected given the feature point. So here that you will apply the logistic function, that is ultimately nothing but the exponential function 1 divided by 1 plus exponential of minus beta t, and then the feature points. And then after, it is quite possible that when you apply this maximum function for different points, there is a probability of the selection to be like more than 0.5 or 0.6. So let's say there are 2 points, one with the probability of 0.85, another is having the probability of 0.91. So both the points are quite obvious to be selected because the probabilities are quite high, almost near to 1. However, what we are trying to do is the point can be the selected. So where we apply this max function from all the selected points to annotate the particular x point. So this is the way for the annotation. And these are the some of the results I just wanted to discuss that we use this PhysioNet database and the manual annotation of these different 9 points. So these are the ground truth which I told you that we spend a week time to manually annotate. So they're consistently having the high outcome. And this is the manual with compared to the automatic annotation using machine learning. So you can see the blue line is the manual annotation, and this red, black, and the green are the annotation using the machine learning models. Although the accuracy is not high as to the manual annotation, but they represent the underlying trend. So that indicates that the machine learning models can be applied to this kind of the problem. Although the accuracy is comparable, but not that high compared to the manual annotation. But if you further analyze this research using this machine learning models, then you will be able to successfully improve the accuracy. So that's what the results for the manual annotation compared to the automatic annotation. And there are some evaluation methods we have applied for the quantitative as well as for the qualitative evaluation. So there are different metrics we have taken, like a precision recall F measure for quantitative analysis, and for qualitative analysis we have taken the time difference error, then time difference root mean square error, and the mean error, cardiac time intervals, as well as the mean response time. And these are the results which can show, you can see that the annotation results with the machine learning and the annotation results without machine learning. This is a conventional approach at the bottom, and on the top the results are for the annotation using machine learning. So you can see that the F score, which is of the point of interest for the ECG, is 0.854, and for SCG it is 0.82. Now the results on the top are for the SCG. So we will be able to compare this 0.82 F score with over here. We can see that the logistic regression is consistently having the F score more than 0.9. As well as we can see the worst model, Naive is also having the F score more than 0.5. That means even if I apply the worst model of the machine learning, it will definitely perform better than the manual, or not the manual, the non-machine learning approach for the annotation purpose of these SCG signals. So that was the interesting part when it comes to the learning the process using the machine learning. So I think these are the another results for the time difference error and the time difference root mean square error, cardiac time intervals, and the annotation. And these are some references we used during our PhD work to in order to gather this understanding as well as the model application. And there are some very good research papers are available in published in very good journals like IEEE Transactions on Biomedical Engineering. So these are the top journals in the given area. So if you read like the scientific reports, so that's a Nature publication. So they have designed this automatic identification of systole time interval in the seismocardiogram. So you may also refer to these references for your understanding of the area, and then after design something which can contribute in this particular area. So with this, I hope to conclude this session. Thank you very much.
Thank you very much, Dr. Hiran. So I request participants, do you have any question or any query regarding the talk given by Dr. Hiran? So Dr. Hiran will with us again on day after tomorrow. So if you have any doubt, then you can ask, or you can fabricate your doubts. You can ask in the later on. Yes, anybody please? Any query, any doubt, anything you want to discuss, please? So I think Dr. Hiran, no response from the participant side.
Okay.
Okay. So thank you, Dr. Hiran, for your nice presentation related to your cardiac healthcare by using machine learning approach, as well as your SCG annotation discussion. Actually, it is a pretty good and pretty analytics way you have explained. So I hope participants should get benefited out of that. So I request all participants, please be fabricate some doubts with your mind if you have. Then day after tomorrow, again, we have a session with Dr. Hiran. So we will discuss with Hiran. So thank you, Dr. Hiran. We will meet again day after tomorrow. Thank you very much for your kind support, and you have spent your valuable time with us. So once again, thank you. Thank you very much.
Thank you, Dr. Hriday Kumar Tripathi, for this wonderful session. I think one of the participant, I don't know
Yeah.
if they have question or not, but of course, on the day after tomorrow, we will discuss if they have some doubts in their mind. I will be happy to answer them.
Yes, yes, yes. So
Okay, thank you very much.
Thank you. Thank you very much. And take care. Good
Okay,
night.
bye-bye.